Okay, today we have our last section of Chapter 6, dealing with analyzing solutions to quadratic equations. We've been solving quadratic equations, but now we're going to use something called the discriminant to help us do that, to determine the nature of the roots and also how many x-intercepts we have on our graph. So to do that, we have quite a few things to look at, so let's get started. You're going to have to remember how to simplify radicals in order to deal with square roots. So let's try a couple of these. Some of them are easier than others, but let's see what we've got. If I take, we've got to get the pen to work here. If we took the square root of 16 and we asked you to solve that, you should be able to. Perfect square. Okay, let's stop for a second. Oop, we got it now. It's just doing some crazy things. So the square root of 16 should be 4. We don't have any other perfect squares listed in our selection, so we would have to, as we say, break them down. Now that's a big 4, so let's go to a regular 4. Here we go. So on 8, square root of 8, most people would think of it as 4 times 2, 4 being the perfect square number, and then 2 root 2. That's the exact answer. That's how we'd like to leave it. On 50, same sort of thing. Perfect square number that goes into there, the largest one is 25. 25 times 2, so that would turn into 5 root 2. And the 128, I believe it's 64 times 2. So you just got to start recognizing some of these and the factors that go into them with their perfect square factors. So 8 root 2. Is everything always going to be root 2? No, that's just one of the easier ones. And in 71, we're looking at, you go right through the list, 4, 9, 16, 25, 36. We're not finding factors of 71 that would break it down. So those kind that you can't would stay the same as square root of 71. Okay, moving forward. A couple of reminders. We have been finding how to graph, and it's been a rough graph, we'll call it, quadratic function. We found the a, b, and c values. We find the line of symmetry. Remember that shortcut for line of symmetry was opposite of b over 2a, and that's the x value. So x equals the opposite of b over 2a because it's our vertical line that shows where our line of symmetry that cuts the parabola in half exactly. Then it says plug the line of symmetry in to get the y coordinate. So if you have x, you should be able to plug it into your equation to get y. And then last but not least, sketch the graph based on skinny or wide the parabola is, based on that a value. So those are things we did roughly, and we used our calculator as well. But today we will learn how to find the solutions to the quadratic functions. Notice I say here I'm going to use the plural of it because it's going to be more than one function. So obviously when we say plural, we're looking at could it be 1? Could it be more than 1? Could it be 2, 3, 4? And we've done enough of these, so we're going to ask you to draw some conclusions. But here we go, starting with a solution to a quadratic, the point where y equals 0 on the graph. This is the point where the parabola crosses the x-axis. So on this one, you'd be looking at it has 2 places where the graph crosses the x-axis. So that's what we're talking about when we say the solutions. So if you have a graph, it'll be easy to see. We're saying, though, based on what we've done with our graphs, we have 3 possibilities. 2 solutions, like we just showed, if it's an upward parabola and it crosses through because the vertex is down below, or if it's a downward parabola with the vertex up above and it crosses down below. Then one option would be the vertex right on the axis, and it could either go up or down. And then last but not least, we have what if it doesn't cross the x-axis at all? Opens up and starts up above, opens down and starts below. Those are the 3 choices that we've seen in parabolas. And remember, parabolas are what we're talking about, open up or down only. From there, You can find solutions or roots to the quadratic function two ways. Accurately graph it. It would take a long time, it says here. No rough sketches like you used to do. You could set the quadratic function equal to 0 and solve it for x using the quadratic formula. Now, we've been working on quadratic formulas, so that should be okay. Since the definition of solutions to a quadratic function says they are wherever the y value equals 0, we can plug 0 in for y into that original equation and find the roots. So we're going to do that with a couple examples. Some of them will be short, some of them will be longer. So let's start here. What if I said y equals x squared minus 9? Now remember, it's looking for solutions, so put a 0 in for y, first choice, because we were looking for where does it cross the x-axis, and the y value would have to be 0. From there, we'd move the 9 over to the other side by adding 9, which would give us x squared equals 9, or 9 equals x squared. From then, we take the square root of both sides, and as you know, x would be plus or minus 3. So our solutions on that one would be plus or minus 3. Now question, what does that plus or minus 3 really mean for the original problem? It means that we take that plus or minus 3 and graph that equation, then we should be seeing a intersection on the x-axis at those 2 points, positive 3 and negative 3. So 2 solutions. Second one, same start, x squared minus 16, so you're going to put your 0 in for y. You're going to move your 16 to the other side. You quickly have x squared equals 16, so plus or minus 4. Again, what would that mean? We would have our graphs with 2 solutions at a positive and a negative 4. What about the next one? And you're going to see this same pattern. You're going to see the same add to the other side, but notice in the original equation, we're used to seeing ax squared plus bx plus c. In each of these that I've done so far, notice that the bx term is missing. That term with just the x, we have a squared and we have a constant. And when that's the case, you're going to get something like we have here every single time. Now, luckily, it's been nice whole numbers, too. And again, if we would graph, they would cross at positive and negative 2 on this one. But that missing, that b middle term, is key on each of these. Next one. And it's just showing the graph of what we just discovered. Now, y equals 5x squared. Now, look at this one. In relationship to what we were just talking about, it only has an a term. It's missing a b and a c value. So put the 0 in for y. Divide by 5. X squared equals 0. So x equals positive and negative 0, which we know means just x equals 0. And we only have one solution. So when we only have that a value, we're going to get this parabola to cross in one spot and one spot only. So again, this one has a parabola and a constant. Let's solve it. Put the 0 in, move the 9 over. X squared equals negative 9. Ooh, start thinking. We've had these imaginary numbers. So x is going to give us undefined or an imaginary solution, because we know in this case that x would equal 3i. And we could say plus or minus 3i because we took the square root up there. So that is definitely not a real number. That's our imaginary. That's our complex. Okay? So what do you want to say? That cannot be graphed on our real number system. So that's a problem. So a question will be now, if you think back, what does it mean to have a solution that's undefined? In terms of the graph, it's the only possibility that does not cross the x-axis. So there is no x-intercept, and it only can occur in 2 ways. When you have a parabola opening up, where the vertex is above the x-axis, or a parabola that opens down, where that vertex is below the x-axis. So we've just gone over the 3 possibilities. So with that, start looking at these. For each of the following, find out how many solutions each one has and what they are. So in other words, you would have to solve them by doing what we just did. And I'm looking at this first one. We have an a term and a constant. Same thing on the second one, an a term and a constant. Third one, we just have that a term. And this last one, we have the a term and a constant. So not one of these do we have ax squared plus bx plus c. That is definitely a pattern that you want to look at. So when they're the shorter ones, you should be able to put the 0 in and move terms accordingly. And just as a brief look, you can take those as your first guide. First look, do the work off of those. So you can stop and pause right here and try to solve those 4. If you do and continue on, the solutions for those would look similar to this. So if you need to pause right now, do that. The solutions for those would be 2 solutions on the top one, both positive and negative, 2. The second one had a negative square root, so it had undefined. Third one, there was 1 solution only, right on the x-axis. And the last one, it also had 2 solutions, but they were positive and negative 5. So we have nice whole numbers here. We had 1 solution, because it really is not a plus minus 0. We know that's just a 0. And then the undefined one, we wouldn't have seen it cross. So quick problems that way. Now we're going to say, well, what happens in the big picture? The discriminant is that value underneath the the radical sign in the quadratic formula. So when we do the quadratic formula and we say x equals opposite of b plus or minus square root of b squared minus 4ac all over 2a. That b squared minus 4ac, notice I don't have a square root over it, those numbers of b squared minus 4ac are considered to be the discriminant. So if someone says use the discriminant, you're going to do whatever the calculation is for b squared minus 4ac. Notice, you can use the discriminant now to determine the equation's number and types of solutions. So looking further here, we've done b squared minus 4ac several times, and it's been a positive number. Anytime it is positive, then the equation is going to have 2 real solutions. We've also done it when it came out, the calculation has actually come out to 0. When it comes out to 0, then the equation has 1 real solution. And last but not least, we've also just seen when we do b squared minus 4ac and it's a negative number, less than 0, which we know means it has 2 imaginary solutions, which means it has 0 real solutions. So we could also say 0 real solutions here. So you're just going to have to watch how the question's worded. How many solutions? Well, if it says how many solutions, you could say 2 imaginary solutions. If it says how many real solutions, you would have to say 0. So it really goes in descending order here. 2 real solutions, 1 real solution, 0 real solutions, because those solutions are actually imaginary. So if I start looking, you should be able to tell these fairly easily which graphs have 2 solutions. So you start looking at the graphs, the parabolas, where the x-axis orientation is, and you should know yes, no, just by virtue of looking. Okay, so you should know what kind of number the discriminant is. If I have 2 solutions, we just said it has to be a positive solution. So we would get a positive on C, on E, and on H. Question, which graphs have no solution? No solution means we're going to get a negative number when we do the discriminant. No solution. Think about what that meant. Oh yeah, we have no place that it crosses the x-axis. So start looking at that. You should have chosen D and F, and that should have been all. And last but not least, which graphs have 1 solution? So meaning right away you know the discriminant came out to be a 0. If the discriminant came out to be a 0, it lands once and it lands right on the vertex point. And you can see we have several of those where we're landing right on the vertex point. So you already know what happened to the discriminant even just by looking at the graph, and vice versa now. So the question is, what is going to happen? So here's an example of just doing the discriminant. So remember, b squared minus 4ac. That's all the math you're going to do. So you have to give you a quadratic. And in this case, I've just given you the numbers. So you're left to do the math. So let's just try a couple of them. We know 4 squared is 16. We know we have to do all of this at once. 4 times 2 is 8, times 1 is 8. 16 take away 8 would leave us with an 8. Okay, if it leaves us with an 8, that's a positive number. Start thinking 1, 2, or no solutions. You should have chosen 2. Okay, let's try one farther down here. If I have 5 squared is 25 minus 4 times negative 2 times negative 8, we know that's a positive. Negative times a negative is a positive. But 4 times 2 is 8. 8 times 8 is 64. And so 25 subtract 64, even if we don't finish the math, is going to be a negative number. And if we have a negative number there, we know we're going to have no real solutions. So you're going to do each one and you're just going to match them. And that means no solutions. It's either going to be a parabola that opens up and is above the axis, or opens down and starts below the axis. If you don't have numbers given to you, you might have the whole entire quadratic. So that's what we're going to look at. How can you use the discriminant to determine the number of solutions for a quadratic equation? Remember, a quadratic equation would look y equals ax squared plus bx plus c, or at least that's what we want it to look like. So that's standard form. And if you don't have your quadratic in standard form, that's job one. Get it in standard form. So rewrite it, because you have to be able to identify what's A, what's B, and what's C in order to use the discriminant. So job one, rewrite any equation you're given in standard form, identify A, B, and C, plug them in and do the math, and find out, do you have a number that is positive, 0, or negative, and how many solutions you would get from each of those. So with that, we should be able to try a few. Here's a whole quadratic ready to go. I can see I have an A value of 3, a B value of negative 4, and a C value of 5. So if we use the discriminant only, B squared would be 16 minus 4 times A, which is 3, times C, which is 5. Do the math. We've got 16 out front. We have to do your choice. 4 times 5 is easy, so 20. 20 times 3 is 60. And if we do 16 take away 60, we get a negative 44. We have that negative number, which means we will have no solutions. No real solutions, that is. It does not cross the x-axis. And so how many zeros would you have? We would not have any. So that's what we expect you to do on a quadratic. And then the only difference here is if it's not in standard form, which none of these are, job one would be to get it in standard form. So on this top one, I would probably move both the 3x to the other side and the 4. And when I do that, I get a big fat 0 on the left-hand side, put it in descending order, 2x squared plus 3x subtract 4. Now you can identify your A, your B, and your C value in order to do your zeros. Okay? And so that's what you're going to get practice in. You're not going to necessarily do the whole quadratic formula tonight. If they say find the zeros, yes, but if all they're looking for is how many and what type are they, because a question might say find the nature of the roots. If they say find the nature of the roots, it really means how many do you have, 2, 1, or none, and what type are they. And so you'd say 2 real solutions, 1 real solution, no real solutions, and instead of no real, sometimes you could say 2 imaginary. It just depends on how the question's worded. So watch that carefully, and I think that's all you need to know. Continue working on memorizing that quadratic formula. It'll definitely help. And now you also have the idea that the b squared minus 4ac part is called the discriminant. So bring any questions you have or problems with calculations to class.